This is our introduction to exercise 3.4 on power functions, page 103 of your textbook. We're going to be focusing on a couple of things. Number one is the difference or the relationship between odd and even positive powers. We're going to be looking at negative powers as well. And then finally, we're going to be looking at fractional powers. Okay? The idea is basically know the general shape of the function. So when you try to input coordinates or input x values, it's going to look a lot more familiar anyway. Okay? And we're going to do a little bit of revision of polynomial division. Do we like that? Or we did it last year though, right? We just didn't like it. Alright, so we'll go through it very quickly as well. Alright, let's start with our relationship between odd and even positive powers. Now, when I'm talking about our polynomials, of course, there are many different forms, right? But the ones we're focusing on for this format is specifically where we have our quote-unquote turning point form, which is this one right here. Depending on, of course, the value of n, so that as the power increases or decreases, it changes the number of turning points. We're keeping this format in mind. Of course, for example, if it's a cubic function, it could look like this, or it could look like this. Yeah, where you have two turning points versus a point of inflection. Okay, but we're going to focus on this format here. The number of turning points and the general shape changes as we see. Of course, translations and transformations, etc. you already know. If it's a negative value at the front, it causes the function to be flipped, etc. you already know that. But the general idea is that as the power increases, the relationship changes. So for example, if I have to the power of 1, of course, I'm sticking with a positive. Of course, I know that if it's a positive, it goes up and towards the right. Pretty easy. If it's to the power of 2, if it's the power of 2 versus the power of 3, I'm going to write these ones over here. So the power of 2, of course, it goes down and then up. We're aware of that. That's positive parabola, smiley face. Third power, of course, it's going to go up, down, and then back up, depending on how the function looks. Is it in point of inflection form? Then it might just look like this, but we're going to focus on just that shape for now. So the power of 4, it's going to look like this. And these, I'm assuming positive, by the way. And if I go power 5, it'll look like this. Oops, let me try that again. Of course, the number of turning points in this format is going to be n, or the power, minus 1. Yeah? It's like, for example, if you differentiate the function, you're going to have 1 less power. Therefore, when you solve it, it's going to have that number of solutions. The thing to note here is that if it's a positive function, we're assuming all positive across the board, if it's an odd power, it'll increase on its first, it'll increase in gradient, a positive gradient in this first section. Same thing here, same thing here as well. If it's even, it'll always go down on its first iteration. Okay, that's a general theme. Of course, if it's negative, then you flip it across. We're assuming positive for now. So just generally understanding the odd and even positive powers. If, for example, we're focusing on this format, a cubic function, as we mentioned, can look like this. What does a quartic function look like if it's in that form? It's just a fat parabola. Yeah, it's just a fat parabola. And as we increase the power, with our even functions, it just gets even fatter. And you note that with the increased power, the higher the power, the more drastically our function changes, and the larger the gradient's going to be. Great. One last thing to note on odd and even positive powers. Please don't mistake them with odd and even functions. They're a completely different concept based off the idea of rotational symmetry. But just for now, focus on odd and even positive powers. Any questions about odd and even positive powers before I move on to the negative powers? Does that sound familiar, what I've covered so far? Okay. So let's look at negative powers. With negative powers, what we're focusing on, of course, is negative power, -1, -2, etc., etc. The ones we focus on in methods are -1 and -2. Right? With a hyperbola, it's going to be -1. This is actually the reason why you can't divide anything by 0. Right? Has anyone explained that to you before? Has Mr. Brother explained that? Why, for example, 5 over 0 is undefined? Yes, no. Can someone please respond? No, okay, thank you very much. I'm going to very quickly go through that. If I have, for example, and I'm looking at a function of y equals to 1 over x, or a hyperbola, if I look at that function as an approach from the right towards 0, so I'm slowly replacing x with numbers that are from the positive side, so 100, and then getting smaller, and 10, and 1, and 0.1, 0.01, etc., etc. As I go smaller, the value of y, or the value of 1 over that value of x, should be approaching infinity, correct? Yeah. However, if we approach from the negative side, we still go towards 0, but as the limit of x approaches 0, from the negative side, our value of y actually approaches negative infinity, doesn't it? So because there are two possible answers, theoretically, it could be both positive and negative infinity. That's impossible, we just say it's undefined. That's the reason. Of course, the main thing to note for this one is our asymptotes. Our values cannot equal, here we go, cannot equal to y equals 0, and it cannot equal to x equals 0 as well. Of course, that's just our base function. As we apply transformations, that can change. The idea that which you, again, are hopefully familiar with already, is that the maximal domain is given by, well, what can it not be? Of course, 1 over 0 doesn't exist, or is undefined, sorry, and so therefore, anything on the denominator, let that equal 0, that will give you a maximal domain, or what you can't have as your x. And then for your y, no matter what substitute for x, you will not get 0. So therefore, in this case, whatever's on the outside, the plus c aspect, would be our asymptote. The graph of y equals to x to the power of negative 2 is 1 over x squared. Of course, it's our truncus, right? I just remember truncus because it looks like a trunk of a tree. There you go. And our asymptotes are pretty similar as well. Any questions? Okay, let's do some revision on polynomial division. Bars. Okay, so show that y equals to 2x minus 3 over 1 minus x can be written in the form y equals to a over x minus 1 plus b, where a and b are constants. So, anytime we present it with something like this, it looks really awful, but we can actually rearrange, transpose it, etc. in order to get something that looks like this, and therefore get our asymptotes very clearly. So, I'm going to do 2x minus 3. 2x minus 3 divided by, and I'm going to write negative x plus 1 instead. I'm just going to switch it around. So, what number multiplied by, let me fix that up. There we go. What number multiplied by negative x gives me positive 2x? Thank you very much. Negative 2. So I'm going to write negative 2. I'm going to write positive 2x here. Multiplying the 1 and the negative 2 gives me negative 2. And of course, whatever I have here, because it's long division, I have to subtract. So that gives me 0 on the left-hand side, and negative 3 minus negative 2, which is negative 3 plus 2, using negative 1. Am I going through that too quickly? Okay. Now, I don't feel that I can fit negative x plus 1 into the negative 1. So, what we're going to do now is we say that this, where we go, y equals to 2x minus 3 over 1 minus x, which we know equals to negative 2 plus, and instead of writing remainder negative 1, I'm going to write plus, or minus, let's just do minus, 1 over negative x plus 1. So it's the remainder divided by what we're dividing by. And we end up with negative 2 minus, or it could be plus and then the negative of 1 over negative x plus 1. I'm going to rearrange that. We get negative 1 over negative x plus 1 minus 2. Sweet, are we done? Why not? Good, it wants x minus 1 specifically in this question, so let's just multiply everything by negative 1, or I could just take the bracket out, and I'm going to do this. Apologies, I'm cheating. There we go. Take the negative out, they cancel out, we end up with 1 over x minus 1 minus 2. Of course, a would equal to 1, b equals to negative 2. Now, it's a lot easier to sketch. It says, hence, sketch the graph of y and state the natural domain and range. Of course, we know that the natural domain, right here, the domain is going to be represented by x being an element of all real values except when you're doing barring or except, make sure you use that slash, the backslash, and then I'm going to write 1. Make sure if you're specifying a singular value, use your squiggly brackets. Our range, our y is going to be an element of all real values except what? -2, good. Because no matter what you substitute, oh, that's an awful bracket, no matter what you substitute for x, you will never get 0 for that fraction, therefore -2. So when we sketch it, it's going to look pretty straightforward. We're just going to go ahead and put in x equals to 1, which is about here, let's say. X equals to 1. I'm going to put in y equals to -2. Apologies, I know that it's kind of crammed. And then I just fill in my function. I know it's a hyperbola, and I also know that it's positive, therefore it looks something like that. In most situations in exam, it'll ask you to label all key intercepts. What intercepts would, sorry, all key features, what features would I have to label in a function like this? X and y intercepts, anything else? Asymptotic equations, good. And if I specify a restricted domain, so if I, thank you very much. If I say, for example, x is only between -2 and 2, you'd have to specify endpoints as well. And in this case, no turning points, we just leave that as is. I'm going to move on to the next section, and this is it. I'm just going to be talking for this part. We're looking at fractional powers. Fractional powers, we're looking at y equals to x to the power of a half, or square root of x, and etc. for cube root of x. The idea that I really want to focus on is it looks very familiar. The only, Jesus, a fly in my hand. There we go. The only difference is that it's kind of like the inverse of our cubic functions, isn't it? If I write, for example, y equals x to the power of 3, and then I inverse it, you end up with cube root of x. So it's related, oh perfect, it says it right there. It's related to our functions, our basic polynomials. The same shape but reflected across the y equals to x. When we switch y and x, we reflect it across the y equals x line, just like in our inverse functions. Don't worry, we'll touch up on inverse functions next lesson. In the case of root x, and any n, let's say we have y equals to n root x, of course, there we go. Of course the function only exists for half because you can't have the square root of a negative number. Okay? So in our function of y equals to, let's look at this one, cube root of x, of course it looks like if I was to put a line here, and that equal to y equal to x, then if I graph the opposite side, it's going to look like this, isn't it? And lo and behold, it's y equals to x cubed function. If you want to see what it looks like in writing, y equals x cubed, you switch the inverse. I'm just going to write f just for the general notation. So we get x equals to y cubed. I cube root both sides, of course, and I get, which is what we are graphing anyway, and applies to all our functions. But the main part, remember, root x or any even number, root, sorry, means that you can't have x as the negative values. Okay. Any questions? Okay.